Hello, everyone. My name is Łukasz Bratasz. I'm head of the Cultural Heritage Research Group at the Institute of Catalysis and Surface Chemistry of Polish Academy of Sciences in Krakow, Poland. And my research focused mainly on the risk of mechanical damage due to the humidity variation, due to the temperature variation to vulnerable works of art, also on the risk assessment, as well as energy efficient methods of the climate control in museums, in archives, and other memory institutions. But today I will not speak about my research and research of my group. I would rather prefer to show how this research can be converted into tools which can be used by the heritage managers and conservation professionals. So let me share my presentation. And as you can see here, these tools are made available on the digital decision support platform, which we also call digital preventive conservation platform, that offers the remote access and free access to quantitative risk assessment for heritage assets. And as I mentioned, my name is Łukasz Bratasz, and here is the email address you can use if you want to contact me. And motivation for this research is stated here, which says that effective risk management and preservation strategy requires identification, which is obvious, and quantitative assessment of the most relevant processes, which are in fact priorities leading to loss of collection value. And this statement, this motivation is very obvious between community working on the preventive conservation. But maybe if some of you have more experience with heritage science focusing on the technological history, I would like to give some examples how the quantitative risk assessment can be helpful in decision making. And maybe I will start to illustrate the use, the need for such a tools with one of the most important challenge for conservation community, for heritage community, which is energy consumption. And one of the most important question is how we really preserve the collections, the cultural heritage objects, but at the same time we will not cause the harm to the environment. So how to preserve the collection, but at the same time keeping energy costs, financial and environmental, at the very reasonable and optimal level. And this graph shows the annual energy consumption expressed in kilowatt hours per square meter in 75 museums all over the world, but more or less in the same climate zone. This is the zone typical for the Northern Europe or for the areas in US like New York, Boston, Philadelphia, or Chicago. And as you can see here, some data are from my private database, which the data I obtained from my colleagues and friends. There are UK data from 2009 from the publicly available data. There is Arup data. This is the construction company, one of the largest construction company building museums all over the world. And there is a building performance database, and this result shows the data from the museums in New York, Boston, Philadelphia, and Chicago, as well as the data from Yale University, where I spent almost 4 years as a head of this, where I work at the head of the Sustainable Conservation Lab. And what you can see here, that this data covered, they span wide range of energy consumption, almost 2 orders of magnitude. So it means that really depends, the energy consumption depends on how we really control the environment. If we control in the very narrow bands of relative humidity, we use a lot of energy. If we have local humidifiers, simple solution, passive solution, we can use many times less energy. And I would like, so we know that we can save a lot of energy. But the question, of course, is what is another part of the equation? What is the risk to the collection when we relax the environment? And I would like to focus your attention on this data, which is the Yale University Art Gallery data, and show the climate. And as you can see here, here are relative humidity variation in the Yale University Art Gallery, which vary between 40 and 60%, which is the range recommended by environmental guidelines of International Institute for Conservation, as well as International Council of Museums, Conservation Committee, and the relative humidity from this gallery falls mostly into this range, with some exceptions here as well as here. But the relative humidity variation is only the first very basic, very rough estimation of the risk to the collection. And much more important is to look at dimensional change, dimensional response of the wooden objects, which we call in this case strain. And it allows to evaluate risk of damage in better and more efficient way. And I will try to show you how to sample this climate using this painting from the collection of the National Museum in Krakow, where I also worked before leaving to Yale. And this is tempera painting on 10mm thick wooden panel, varnished from one side. So it means that diffusion penetrates only from the back side, but the front side is blocked. And to analyze the strain history, the dimensional change history, we developed the computer model in the finite, one of the typical softwares for finite element calculation. And we, of course, put a lot of relevant parameters, all relevant parameters, material parameters, and we calculated the strain. And here you can see data. Here there is a strain history, and the strain history is compared with the strain history in the gesso layer, which is the animal glue-based ground, which is the most brittle part of the paint layer. And it is the strain history in the gesso layer is compared with the critical values at which beyond which the gesso can be damaged. And as you can see here, there is the strain history is very far from any risk, and it means that there is no risk, and there is still a lot of room for relaxation of the environment without bringing risk of mechanical damage to works of art. So we know that the strain history is very good measure of the risk, but it has some drawbacks, this approach, because to do that you need large computers, because this calculation require large computational power, are usually time consuming. So even using the good computers, you need few hours for calculation and require specialized expertise and programs. And I have to say that I know I don't know if I know any museum which has this competence, but large museums, leading museums in the world, at least they have the network of collaborators, so they have access to the expertise, and for them this risk could be calculated. But the medium-sized or smaller museums, or the museums which are not leading museums, they have really there is a barrier in access to this expertise. Therefore, we proposed an alternative approach, which is based on the website platform. So the user uploads the environmental data, temperature and relative humidity data. Climate is decomposed into elementary sinusoidal range variation using a fast Fourier transform. And there is a large database for which the elementary strain variations are calculated in response to each sinusoidal range variation. And this database it sees on the website and is collected there. And this elementary strain variation were pre-calculated for the sine functions of various amplitude, of various duration, but also on various levels, for different types of the objects, for different types of the woods, for different thicknesses, for different direction of the moisture diffusion for different geysers and for different temperatures as well. And when this climate is decomposed, then knowing the elementary strength variations which are calculated and stored in the database, they could be called and fused into complete object response. And the benefit of this approach is that the strain history can be calculated within few seconds. Here is another example related to risk of fire. I think that there is no need to convince anyone that fire is still one of the largest risks to collections in museums, libraries, and archives globally. On HERIe platform, we have implemented a tool allowing to evaluate, to estimate the risk of the fire for different types of buildings, for different types of the collections and their vulnerability to heat and combustion, also to collections of various vulnerabilities to water, as water is agent frequently used for extinguishing action. And using this tool, you can estimate estimated loss of the collection value. But I would like to show how the tools available on the platform can be used to select the optimal fire protection system, not the best one, but the optimal one. I will show that with the example of the Central Museum storage in Warsaw, which was built for several museums in the central Poland. This is the one-floor building built according to the concept of the passive climate control, so it uses very little energy. During the design of the central storage in Warsaw, it was a very relevant question for entire designing team. Where is the optimum between the preservation, between fire protection and the increasing costs? And the question was, are the costs justified? Here you can see estimated loss of collection value calculated for that building expressed in percent of the lost collection value per 1 year. And the estimation was performed using methodology proposed by Jean Tétrault from Canadian Conservation Institute. And we performed this estimation as a function of the class of the fire protection. So we started from the lowest class 1 and we go up to highest class of fire protection 6. And we performed the estimation for materials of various sensitivity to water, medium and high sensitivity to water. We also included information about probability of unwanted activation of water-based fire suppression systems, like for example sprinklers, which are another source of damages to collections vulnerable to water. The information about unwanted activation was obtained from the National Fire Protection Association of United States. We also estimated the loss of the collection value for the situation when the gaseous fire suppression system is used, which of course doesn't affect the materials which have high sensitivity to water. Classes 1, 2, and 3 don't require automatic extinguishing system, so information about the unwanted information is irrelevant. But it starts to be relevant when we go to the classes higher than 4. Then is quite clear trend in the estimated loss of the collection value. So maybe with the exception of first 2 classes, when we increase the class of the fire protection, we decrease estimated loss of the risk of fire by 1 order of magnitude. But at the same time, when we calculated how the costs increase, you can see here they are marked with the red color. The increase of the cost is quite substantial. When you go from the class 1 to class 6, you in fact increase the capital cost of the investment by 30%. Finding solution to this dilemma is not obvious, and probably there is many ways to make a decision, but at least some information and help can be obtained when you compare the risk of the fire with the other largest risk to the collection. And in this case, this is the risk of the chemical degradation of objects which are chemically unstable. And also on the HERIe website, on HERIe platform, there is a tool allowing to calculate these risks. Here you can see comparison of losses caused by the risk of the fire with the losses caused by the chemical degradation, and the orange area shows estimated loss of the collection value for materials of low vulnerability to chemical degradation, like for example high quality paper stored at 20 Celsius degrees and 50% of relative humidity. But because the central storage in Warsaw, it would be cool storage, so we also estimated the losses for the temperature 8 Celsius degrees and 50% of RH. As temperature in a storage will change seasonally between 8 Celsius degrees and 18 Celsius degrees, so the losses, average losses, are expected to be between the green and the orange areas. In conclusion, for low classes of the fire protection, the lifetime of the collection is determined by the risk of the fire, and when we increase the fire protection, the situation improves, but only to the certain point. When the losses of the losses caused by chemical degradation are larger than the losses caused by the risk of the fire, the further increase of the fire protection doesn't increase the lifetime of the collection, and from point of view of investment of limited resources, such action is questionable. I hope I have convincingly demonstrated how the quantitative information about the risk and their impact on the collection value can be used to support decision in the field of preventive conservation. In this case, I have demonstrated how the comparison of impact of various risks, fire risk and the risk of chemical degradation, can support decision, can inform decision about selection of the adequate, most optimum class of the fire protection. And so this is the motivation, and the HERIe, we call this digital preventive conservation platform HERIe, is available for everyone for free at the address herie.pl. So please use, you just only to register. And this database, this website, this preventive conservation, digital preventive conservation platform was developed within the IPEON HS project, which is focused on integrating platforms for European research infrastructure or heritage science, and it was developed with the financial support of the Getty Conservation Institute. And as you can see here, there is a few institutions participated in the development of the database, but also another institution participated, contributed to the conceptualization of the platform, and so on. The structure of the platform follows the framework of 10 agents of deterioration proposed by the Canadian Conservation Institute. So those 10 agents are incorrect relative humidity, incorrect temperature, fire, criminals and vandals, pest, contaminants, radiation, water, physical forces, and dissociation and curatorial neglect. Those agents which are highlighted in the white, they already contain the tools for estimation of the risk. Those which are gray, we are waiting for the new tools to come. So far, we have 6 modules, 6 tools. One is mechanical damage due to the environmental variation, and we have 3 types of the objects, like the restrained wood, panel paintings, and the parchment. We have tools for chemical degradation. So generally, we calculate the risk due to the depolymerization of the polymers, and we have the damage function for paper developed by Matthias Sterlitz and his colleagues, Mikalski for general materials, and Image Permeance Institute for cellulose acetate. And we can calculate in this model both the relative lifetimes, frequently called also lifetime multipliers, as well as the lifetimes for those materials. We have module develop for risk assessment of fire, and the data and conceptualization was done by the Jean Tetroff from Canadian Conservation Institute, but my institute, HERIe Institute, developed the calculation engine for it. And we have module predicting indoor concentration of damaging gaseous pollutants from external sources, developed within the European project Impact. So what you need to know is just a material which was used to construct your museum and the concentration in the outer air, and from that you can calculate or estimate levels indoors. So it is a tool for the small user which doesn't have the indoor instruments measuring, equipment measuring that concentration. We have light damage calculator developed by Stefan Mikasi from Canadian Conservation Institute, which is based on the single point measurement and extrapolation. And now we have also new refined version of the light damage calculator developed by Eric Hagen from the Canadian Conservation Institute. In near future, new tools will be available as well, like indoor generated pollution module developed within the European Commission project Memory by David Tickett and his colleagues. We will have full finite element modeling for mechanical damage, as the module which I showed you has some limitation. So for example, it cannot be used in the very warm climate, or humid climate. So if the temperature is above 30, our module so far doesn't work. So it significantly overestimates the risk. And we plan to develop also the module which would enable user to calculate the soiling of objects and surfaces by indoor particle pollution and deposition. We have also new module for upload and processing environmental data, and particularly this processing of environmental data was broadened, so the user can upload 2 data sets and combine them, which reflect and then evaluate by other modules, for example, risk of mechanical damage. And this situation reflects the situation when one museum loans the object to another museum. So you combine the climate from the loaning institution and from the place where the object will be exhibited, you combine, and then you can evaluate the risk. So this module was particularly developed for registrar working in the museum. A few words about the users. So far, the main users are collection managers and conservators. Heritage scientists is quite a large group, but surprisingly for us, also educators. Educators teaching students, making courses, they use the tool extensively. So far, we have more than 500 unique users and more than 2,000 climate data were uploaded. And here is the list of the institutions which supported financially development of the platform, and I would like to thank them all.